How's it going, guys? So I know I said I wasn't going to be streaming today, but uh, I got back pretty early from out of town and everything, so I decided that I would just stream today because I also looked into the problem that we were having yesterday, and I think I figured it out. So I want to take a stab at it, see if we can get it. How's it going, Hilbert Curve and Flare YouTube? I'm doing good. How are you guys? And it is a good morning. I literally just woke up, so. But yeah. So in the last stream I ended and I had some problems with the chunk generation and I got that fixed up too. So it is looking right now. I think it was just issues with the way it was laid out in memory. So, well, maybe I fixed it. I thought I fixed it. I guess not. So yeah, this is something else that I got fixed too. But for now, we're going to focus on just optimization of the size. And yeah, voxel riffs, I wasn't going to do a stream today, but I got back early, so I decided that I would just stream today. And I've got to get some random streams in too, just so that Twitch, I can get the affiliate position or whatever from Twitch. So I think it's 7 streams in 1 month, and I'm at 5 now. So we'll have to see how that goes. Yep. How's it going, Asher? And I did wake up early again today. I mean, it's not too early. It's 9 o'clock, so I usually wake up at 7, but I was up till midnight last night, which is way later than I'm usually up. Which I know is probably different for you guys. Okay, cool. I'm glad you guys enjoy double stream though. Okay, so yeah, in last stream we had a problem because I was accidentally taking up 30 gigabytes of RAM, and that is definitely not good. So I watched a video. Hobson actually had a really good video, which was exactly what I needed. So if you just look this up, he literally has voxel game mesh optimizations, and then he goes through and he basically just talks about how he reduces the size of his voxels. So this is what I followed, and I modified the things that he did a bit, and I'll sort of show you guys what I'm gonna. Yeah, Hobson is great, and I'll show you guys what I think I'm gonna do to reduce the size. So if we look at shader, or not the shader, but the vertex right here. So this is what I'm using right now, and this is horrible because it was taking up 30 gigabytes of RAM. So yeah, and you've seen that one too. Okay, cool. So I knew I had seen it before, so I was like, I know there's a way to reduce the size, I just didn't know how. But yeah, so basically the way this is currently, this is 3 bytes. This is 2 bytes. Or actually, no, not 3 bytes. This is 3 times 4 bytes, which is 12 bytes, because one float is 4 bytes. This is 8 bytes, and this is 4 bytes. So problem with this is it's not that big. Just 12 plus 8 plus 4 is 28 bytes. But once you get into chunk sizes, I think that's right. 12 plus 8 plus 4, 24 bytes. Okay. So once you get into chunk sizes, this is times 16 times 16 times 256. Well, that's still not a whole chunk because we're not even counting all the vertices that you might have. So then you also have to add in times 24 because you could have 24 vertices per cube since you have to duplicate vertices and everything. So this is what you end up with, which is if you divide, that's 36,864. This is kilobytes. And then if I divide that by 1024, this is 36 megabytes, which still isn't too bad, but then you multiply that by 4 by 4, and now you're up to half a gigabyte. And so I tried a 16 by 16 area or something, and it got up to 30 gigabytes, which is not good. And I did sleep okay. It was actually pretty good sleep, so yeah. But this is not good. So basically, if we can reduce this to 32 bits or just 4 bytes, which I think I can, then we can reduce this to half a megabyte per chunk. So if we can reduce this to 32 or 4 bytes times 16 times 16 times 256. So we do that, and then we multiply by 24. So this is per chunk if we had the worst case scenario. And if we divide by 1024, that's kilobytes, 6 megabytes. So we just reduced it by 500, which is great, magnitude of 500. So this should be fine. And if we get in a 16 by 16 chunk area, we're still only using up 1.5 gigabytes, which isn't the greatest. So we may have to reduce that even more if my math is right. I might have done something wrong there. So yeah. And are my blocks each individual faces right now? Is one not one big mesh? No, it is one big mesh, but the way I'm doing it is I'm just allocating enough space for all the vertices, which is probably stupid. So I might do a combination of things. Like this is one thing, and then Langors was mentioning yesterday that I should probably have it be like only store the vertices that I actually need, because I'm just storing like the amount of vertices that I could use, but not nearly all of that is being used. So it's a big waste of space, and I'll have to see how I feel about that and stuff. Anyways, though, we'll reduce this to 32 bits, though. The way we can do that is position is only going to be, I'm going to switch to my drawing screen because I've got that right here. So right here, you can sort of see that our position is just XYZ, and X goes from 0 to 16 within a chunk, Z goes from 0 to 16, and Y goes from 0 to 55. Well, we can get 0 to 16, and technically it's just 0 to 15 or 1 to 16. We can get this with 4 bytes, right? Yeah, or 4 bits, not 4 bytes. So this is 4 bits, and then this is 32, 64. So this is 8 bits, double that, and then this is 4 bits. So in total, we just need 16 bits for the position. So we can reduce that. For a texture ID, I said that I would allocate 13 bits, which is 8,096 different textures. I imagine that that's going to be enough and we'll never run out, but I could be wrong. For the normal direction, like which face of the cube this is, we can store that with 3 bits. And then to figure out where the position actually is in the world, we can just do a uniform and upload the chunk position via uniform. And then this gives us 32 bits, which means we can store all this in 1 byte, which is way better. So that is the plan. And I'm going to switch back to the screen. Okay, cool. So yeah, that is the plan. We'll see if we can actually get that. We'll have to do some like bitwise operations in the shaders to extract all that information and everything and see how that goes. Okay, so we're going to change this to just UN32. And this is just going to be, I guess, data. So, and it's going to store all of this stuff. Oh, and I also didn't have the texture coordinates in there too. For now, I'm going to leave the texture coordinates right here because I'm still not sure what the best way to do those would be. Yeah, so that's going to bump up our data to probably 64 bits per chunk, which is a little bit annoying, but we'll see. So yeah, we'll do that, and then we can get rid of this, and we should be able to get rid of this for now too. So I'm just going to remove those, and we're going to hopefully not break everything. So then I can go into here, and we're just going to change up the way that this works, which is right here. So instead of doing this, I'm going to say I pointer, and this is going to be 1 GL unsigned int, and then this is just going to be offset 0. Yep, which is just offset of vertex data. Okay. And how's it going, CGO Clan? I do remember you from YouTube. I hope you're doing all right as well. Okay, and then we also don't need this normalized position because this is an integer. And for this one, this will still be UVs, so I'm okay with that for now. We'll have to get rid of this, and I have ideas on how we could get rid of this too, but yeah, I'm not sure. Oh, yeah, the text ID. That is how I was going to get rid of this. The texture ID should give us texture coordinates. I'm not sure how to encode that information yet, though, so we'll have to see. But yeah, we can basically do this. And I got to think for a second. It's still kind of early. So now we got to figure out a way to upload all that data just as is. So instead of, okay, so when we load a block, this is when all of that stuff happens. Yeah. So instead of it doing it like this, what we're going to do is this position is a position in world coordinates, and we want that in not world coordinates, but local coordinates to that chunk. So, yeah. Do you want to donate, but you wish your purse was as full as your knowledge? Don't worry, CGO clan, it's fine. I don't need any donations right now too. So, okay, so when we generate the chunk, we basically add in all the IDs and stuff. Yep, that's fine. And then we have the world chunk Z, world chunk X, but we're not going to be doing that now. Instead of that, what we're going to do is we're going to use the position, and we're just going to use the X, Y, Z's we get here, which will range from 0 to 256 or 255, 0 to 15, 0 to 15, which is good. So we can remove this, and I'm actually going to also do this a little bit differently too, because you'll notice I was adding 0.5f to that, so these weren't aligned on integer boundaries. It was like, technically a block was like negative 0.5 to 0.5, and then like same on the left and right, and then the back and the front. So instead, what we got to do is basically make it so that this is all just like aligned on a boundary. So instead, we'll just have like X, Y, Z, and then this will be like +1, so it'll be like 0 to 1, 0 to 1, that type of stuff. So it might be a little bit harder to go backwards, but I don't think it should be too much of a problem. Okay, so anyways, we'll do that. And we're gonna have to change up the way this is working a little bit. So these are only gonna be stored in the first 16 bits. So we gotta do some fancy bitwise operations here to get that to work properly. So I guess I could just do like a, we'll say data equals, and then I kind of want to just encode all this information at once. Yeah. For now, we'll just say that this is a bunch of GLM vec3s, and then we'll convert those as we're uploading it to the actual vertices array. Thanks for YouTube. How's it going, Jan Poon? I hope you're doing well, and I hope I said that right. Okay, so we've got all these vertices, and I'm just going to change this up to this. I guess this should just be like positions now, not vertices, but it's fine. So we'll change up this as well, and that. Okay, cool. So now we should be aligned on integer boundaries and everything. That should be good. And then right here, I'm going to have to change the way that this load block function works. It's not going to take in vertex anymore. It's going to take in reference to a GLM vec3. Yep. And I also have to change the definition of this up top where we declared it forwardly right here. So we're going to switch that out. And okay, yeah, so going back down here, we have no problems now. We have no problems throughout all of this. We just have to fix the actual load block function, which is basically going to smush all this data into a 32-bit integer so that we can sort of extract that on the other side in the shader. Yeah. And you're new to my channel on Twitch and don't know anything that I'm doing. Oh yeah, I'm making Minecraft, so should be cool. And you don't need to say Flare YouTube if you don't want to. You can just say Flare Andrew. Okay, thanks Flare or Andrew. I'll just say Flare or Andrew every time now. Just kidding. Don't worry. But yeah, so we've got all this. We're going to smush it all into one 32-bit integer now. We're going to get rid of elements completely because there's just no reason to have that since I'm duplicating vertices and stuff anyways. So let's be proactive and do that right now. And I'm making a big mistake here because I'm doing all of this at once instead of taking this in steps. And we've seen how that turns out before. So yeah, this probably isn't a very good idea. I probably should have broken this up a little bit, but it's too late now. So we'll take that out. I do have all this stored on Git. So if it goes horribly wrong, I can just git stash all of this and then retry, which hopefully we won't get to that point though. So we're going to remove the elements and that stuff. So this is all we should need. And let's go down here. Yeah, so we're just going to remove that. No more checks for that, I guess. Take out all that stuff. And I guess I'll move that all to the same line since we can. We can remove all of that. And same thing here. Maybe I'll keep these down there. It just makes it reading it a little bit easier. Remove that stuff. Remove this stuff. And this stuff. Almost there. And I think we just got a couple more sides to do. I really should just make like some sort of function to do all this, since I do it the same exact thing like 10 times there. Technically just 6 times, but I should still probably make something for that. Okay, let's remove the element size and bytes, and let's also remove the elements. We don't need that. So let's go back into chunk.h. We're going to remove elements and remove element size bytes. So that should save us another huge amount of memory, because that was taking up quite a bit of memory too. So yeah, that'll be good. And then we'll just have to have like number of arrays, I guess, because I think it's technically draw arrays, but you're just drawing each vertex. So that's like the number of triangles you have. Well, I think this is just number of vertices. Let's call it that. And that should be good. Yep. Anyways, though. And I'll see Asher. Thanks for coming. And how do I feel when the chat interface interacts with me and helps me? It's cool. I like it. Sometimes I don't look over enough, and so I'll miss something whenever you guys like tell me, hey, you can just do this or whatever. So I should probably check it a little bit more often, but you know, it is what it is. It's definitely helpful to have like a bunch of other pairs of eyes looking at my code and stuff, just in case I'm doing something stupid. So yeah. Okay, remove that too. Okay, and so now when we render, we're not going to do draw elements. We're going to do draw arrays. And we can still do triangles, but then we're going to do, first is going to be 0. I believe that's how this works. And then count is going to be render data dot number of vertices. Okay, so that's how it should be. I think that should be fine. Which is also going to be render data dot number of vertices equals chunk width times chunk height times chunk depth times 24. And I guess technically we probably shouldn't do this. We should probably count the number of vertices that we actually have, so that we don't end up duplicating them and then drawing bad data. So I'm going to have to fix that. Yep. And what setup do I have, like PC parts? And I do have 2 monitors. I actually have like a third, like a drawing tablet and everything. And then I've just got like, I think it's an Intel i7, maybe an i9. I can't remember. And then like a RTX 2080. And I got a bunch of RAM because I was getting sick and tired of my computer not having enough RAM. So yeah. But it's a pretty basic setup. I just followed one of the guides on like PC gaming guides or something and built it like that. So yeah. And what language was my first contact for programming? Was it Python? Oh, for you it was Python. I was actually JavaScript. So that's the language that gets a lot of hate. And every time I go back to it, I can't really code in it, but it was good first programming language because it's easy to see what you're doing with websites and stuff. So that was pretty cool. Yeah, I actually learned from a book too when I first started learning programming, because we didn't have internet connection or anything. So I just had a book and a computer that doesn't have internet and just sort of sat there and worked through the book and tried to copy what he was doing. So yeah. And you have a crappy PC and you want to follow me, but you can't because of your crappy 10-year-old PC. That's not an excuse, because like I said, I had a computer that didn't even have internet connection and still learned to code and stuff. So I try to give alternative methods to coding other than using something like Visual Studio, because Visual Studio uses a lot of RAM and everything. So like for the Minecraft series I'm going to do after this, I'm debating whether I'm going to do it in Visual Studio or do it in Visual Studio Code, since that is really lightweight and most people should be able to run that. Or if I'm just going to show how you could do it with Visual Studio Code if you need to do that. So, you know, I'll see how I go with that. I think I'm going to probably show how to use it and then just end up using Visual Studio since it fits me a little bit more. But yeah, please do it in VS Code. I'll definitely show how to do it in VS Code, so don't worry. Okay, anyways, though, we should probably count out the number of vertices as we're doing this. So we can do that pretty simply just by saying here, render data dot number of vertices plus equals 4. Oh, and I guess we kind of store that inside the vertex cursor. So maybe we don't need to do that. We can just use the vertex cursor. So we can just say render data dot number of vertices equals vertex cursor. And that should be good. Cool. So that should store the number of vertices so that when we draw it, we're still drawing good things. If this all goes well. I have no idea what's going to happen when we first do this. So yeah. But your PC doesn't run well, VS well, because you only have 3 gigabytes RAM. Yeah, Visual Studio it's ridiculous when it comes to RAM and stuff. So I definitely understand that, and I'm going to show like Visual Studio Code, how to use it and stuff. And also, I think if you watch like Handmade Hero, Casey Muratori, he gives pretty good description of how to use like Emacs and stuff, which is super lightweight and requires almost no RAM. So that's really nice. It's just, it doesn't have all the features that you get with something like this. So yeah. Anyways though, so now we're going to be not creating an element buffer object because we don't want to do elements. We're just going to have an array buffer on the GPU and then just these 2 things. For now, I'm keeping this until I figure out how to do that. Okay, and then down here, this is where all the magic is going to happen. So we need to smush everything into a 32-bit int. So this is going to be our vertex data, right? And so what I'm going to say, and I don't have that, right? Oh, I do have that. So I can't call it that. We'll call this just our data. So the way this is going to work is bits 0 to 4 are X position. Bits, so then the next 8 bits, so 5, oh, this is 0 to 3. Bits 0 to 3 are X position. Then the next 5 bits, so, or 8 bits, I'm sorry, 4 to 11 is going to be Y position. And then bits 12 through, and I'm going to space all these out so that it just makes sense. I guess I probably should do this. Okay. There we go. Cool. So then bits 12 through the next 4 bits, right? So 15 are going to be the Z position. And then bits, text ID is going to be the next 13 bits. So that's going to be 16 through, what's 15 plus 13 is 28? Yeah? No, 29, I think is what I'm going to have to use. That'll be our text ID, which we'll figure out in the future how to use that. And then the normal direction, which is going to be the next 3 bits. Yeah, which is just 30 through, no, 31. So this was 28. That should be. And that should be 29. Yeah. Yeah. Okay, so that's good. Okay, and that will be our normal direction or just our face value. Like top face, left face, right face, back face, or whatever. Yeah. Okay. And Fudge Raccoon says, "Hey Gabe, when's the series for this dropping on YouTube?" Once we get this in a pretty good position. So we've got chunks loading, we've got some basic ambient lighting. I want to get some transparent objects, get an inventory system, and then get some basic physics working before I even attempt to upload this to YouTube, because I want to actually have a Minecraft game that you guys can build. Like, all the videos I've seen on YouTube of people like, oh, I coded Minecraft. It's like they just coded generating chunks and stuff, which, yeah, that's hard, but there's a lot more to the game than just generating some chunks. So, and biomes even too, right? There's like inventory management, UI, all that stuff, which is pretty difficult. And if you ignore that, that's ignoring like half the game. So not even like 3/4 of the game, right? So yeah. But Flair, you say, do you have any tips for you to learn programming easier without struggling to do things without tutorials? You're going to struggle. So unfortunately, that's just the way it is when you're learning and stuff. But that's good. The more you fail, the more stuff you learn how to do. Like, I've spent so much time just debugging problems and stuff, and it helps you learn a ton because you gain experience, and then the next time you see a bug, you're like, oh, I've seen something like that before, and you can debug it way faster. And once you get a job and stuff too, that'll be really helpful because you'll be much better off than the guy who got his master's degree but didn't really ever code much. So you'll have more experience, and that just helps you out a lot more when it comes to real world stuff, you know? And awesome. I'm glad you're looking forward to the series, Fudge Raccoon. And Hilbert Kirby said, I feel like coding Minecraft clone is like a game dev's milestone. Yeah, it is. That's true. Or at least like a low level game dev's milestone, right? Because they like to do this type of stuff. Okay, so anyways, we've got all of this stuff coded out. Now we just need to put it into the appropriate bits. So let's actually probably go to the drawing screen just so that we can get this figured out pretty easily. So I'm going to switch this over real quickly. Okay, so I'm going to write out like a 32-bit thing because this is just going to make it easier. So we've got 1, 2, 3, 4 bits. Then we got 1, 2, 3, 4. So that's 8, 12, 14. No, 12 plus 4 is 16. 20, 24. And those are all zeros. They look like sixes, but they're not. 28. 32. So we should have 1, 2, 3, 4, 5, 6, 7, 8 sets of 4. Okay, cool. So I said 0 through 3, and I'm going to assume that 0 is the left-hand side, and this is bit 32, or I guess bit 31. So 0 through 3 is going to be X position. So these 3 are going to be X position. And then we're going to have 4 through 11 be Y position. So 4, 5, 6, 7, 8, 9, 10, 11. So these ones are going to be Y position. Then we're going to have 12 through 15 be Z position. So 12, 13, 14, 15. That doesn't make sense, does it? Because that's 4 bits. Oh, yeah, that does make sense. I said I needed 4 bits. Okay, never mind. So 12 through 15 is going to be Z position. And then we're going to need 16 through 20 as the texture ID. So 16, 17, 18, 19, 20. 1, 2, 3, 4, 5, 6, 7, 8, I think. Right? 16, 17, 18, 19, 20. 1, 2, 3, 4, 5, 6, 7, 8. Okay, yep. So these, I might have miscounted that, are going to be text ID. Because we should only have 3 left, which are the normal direction. Let me just double check this one more time. This should be 11. How many bits should that be? That should be 13 bits. So do we have 13 there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yeah, there's 13 there. Okay, so maybe I just miscounted. These will be our normal direction, which I guess we have 4 bits. Oh, that's because this is wrong. Okay. Let's restart real quickly because I messed up the very beginning, which is important. We have to have this working just right. Otherwise, it's going to screw up everything else. So back to here. And did you guys tell me that in the chat? No, it's okay. Okay, so this is going to be X position. Then 4 through 11 are going to be Y position. So 4, 5, 6, 7, 8, 9, 10, 11. Yeah, this makes more sense too. Y position. Okay, then the next 4 are going to be Z. Then 16 through 28 are texture ID. So 16, 17, 18, 19, 20. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this is going to be texture ID. And the last 3 are going to be normal direction. We could probably make this easier if I made this 12 bits, but we lose half of our texture faces. So if I made that 12 bits, then we'd only have 4,000 texture faces. And I think I'd rather have 8,000. So yeah, we'll just have to deal with it. Okay, anyways though. So how do we extract all this information using bitwise operations? Well, we can just use bit masks to extract certain fields, right? So if we want to get the first 4 bits, I think that's just 0xf would give us these 4 bits. Because that is 15, which means we would get 1, 1, 1, 1 here. So if we and this and this, we should get X position. And then to get these 2 bits, we would have to do 0xff0. This should get us these bits. To get this one, we would do 0xf0, 0. So we got 1, 2, 3 zeros. That should get us Z position. So we can just do bitwise and with these guys. This one's a little bit weird. So we're going to have 1 and then FFF 0, 0, 0, 0. So we'll have 0, x, 1, f, 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 and then 4 zeros, 0, 0, 0, 0. Right? Yep. 1 and then f, f, f. 1, 2, 3, 4 zeros. That sounds right. Okay, cool. And then for this last one, this is the last 7 or the last 3 bits, which is, okay, so that's 1, 2, 4, 8. So 2, 4 is 6 plus 8 is 14. So that would be E. So this would be like 0xe. And then we would get zeros for the rest of it, which would be 1, 2, 3, 4, 5, 6, 7, which should be the same here. 1, 2, 3, 4, 5, 6, 7. Yep. So we have 1, 2, 3, and then 4, 5, 6, 7. Cool. Gonna put some dividing lines just so we can see that. Okay, cool. So bitwise anding each of these should get us the appropriate bits. We'll do some tests to make sure that that is true, but I have confidence in that, hopefully. So let me just switch the screen back real quickly. Okay. And you guys said, okay, cool. So it looks like you guys are good. Okay, anyway, so we should be able to use those bitwise operations with those hex values, and it should give us what we're looking for. So we can say like data and equals, and we're gonna have to basically get our position to go from 0 to 255 and everything. So right now, vert1 dot x is probably a float. So first of all, we should change that. So these are ivex. So we're dealing with integers because that will make things way easier. So scrolling up to here, I'm going to change all of this to be ivex and scroll back down to here. And we are going to make all of these ivex. Yep, and that should be good. And then we'll just make this guy an ivec as well. And we're going to change this to be just XYZ. Okay, cool. So that should be good. What's wrong with this? It says no operand matches ivec and vec. Well, this should be, oh, and we should make this ivec too. Okay, cool. So now we're dealing with integers, which is going to be good because that's what we want. And why does the value y need 8 bits instead of 4? Because y goes from 0 to 255. So that's height of the chunk, and then 16 by 16 is width and depth. Yep. Okay, so we've got all that, and then to get that into the appropriate places inside of our data, how do we do that now? We can say data or equals. So the bitwise or operation is going to add these bits to it. And then we should be able to say vert1 dot x and 0x f. So this is basically the idea. I just have to think about this for a second and make sure that this is actually going to work. So if x only goes from 0 to 16, we shouldn't lose, or 0 to 15, we shouldn't lose any information with this. I'm going to do some testing just to make sure that that is true, but I believe we should be good. So then we can say data or equals vert1.y and 0x ff0. Data or equals vert1.z and 0xf000. So that should be good. And then we can just, oh, and then we have to do that for, yeah, vert2, 3, and 4. So all of this stuff. Okay. So basically we're going to have to redo this. So I'm going to extract this just a little bit more of a function to make this a little bit easier. So let's make a function which is static uint32 compress, and this will take in a vertex, so glm ivec3. It will take in a texture format, so texture, and it will take in a cube face. Cool. So if we just do that, we should be fine. And I also have to remove this stuff because we're no longer using that. Okay, so yeah, what's wrong with this? Oh, I gotta add in an implementation. Cool. So we'll put this inside of here. That way it's just all a little bit easier. So we do that. This is now going to be vertex, not vert1. And Oh, this should be a vec3. Okay, cool. So that's bits 0 through 15. We have those sorted out, hopefully. Now we need to do the texture ID, which should be stored inside of the texture itself. And how do we set up the texture too? I think the texture does have like a, okay, so it's just got UVs. We're gonna have to add an ID to our texture format too, and we'll set that up later just so that this works right. And technically we can only have 13 bits for it. So I'm gonna make this a uint16, texture, we'll just call this ID. And we'll make that better in the future because this is only going to have 13 bits. The first 13 bits are actually going to be stored on this, and then the last 3 bits are just going to be garbage. So that's fine. But yeah, so we'll do that. And then if we go back into chunk.cpp, we should be able to say data or equals texture.id and 0x1 fff and then 1 2 3 4 zeros. And then lastly, the normal, which is just the cube face, which if we look at cube face is just 0 1 2 3 4 5. So that's perfect. We already have this sort of bitwise operator. So we should be able to just literally OR it with the cube face, and that should be fine. And this is extending a uint32. Instead of doing that, I'm going to extend this from, I mean, yeah, that's fine. Okay. So then if we go back into where we were, right down here, we can say data or equals cube face and 0xe 1 2 3 4 5 6 7. Okay, cool. So that should hopefully give us what we want. What's this say? We're going to cast this to a uint32. We should be good. Okay, so hopefully that will give us what we want. And we'll just do some testing to make sure that it does. So I'm going to make an extract function just to make sure that this is working the way I think it does. And then we'll compare results. So we'll say static, I guess vec3, ivec3, extract position from a uint32 data. And then we'll just sort of do this and then make sure it all matches and stuff. And once we're sure that it matches, we can remove this stuff. And then we'll have a static, what's it? We got texture ID, int, or I guess this is just a uint32. Is that what I made it? If I go back into here, uint16. Okay, that makes more sense too. Extract text ID from data. And then we'll have a static uint32 extract face from data. Yeah, so what I'm going to do here now is basically we're going to load in all the data here, and then we're going to also extract it back out and make sure that it gives us the same result. If that's true, that means we're storing it in here fine. So yeah. Then what we can do to reverse this process is we can say uint, well, I guess we could just put these all in the uint32s. It doesn't really matter too much. We could just say return, and then this is going to be data and 0xf, data and 0xf f0, data and 0xf000. Okay, and that should give us the position because that's how we stored it here. And then right here, we should be able to say return this, except this is going to be data now, not that. Oh, and this might be a problem. Yeah, I think this is probably going to be a problem. So, because we basically need texture ID to be over here. So we need to shift it left 4. Basically. I think we're going to have to do some bit shifting and stuff too, because that makes sense. Yeah. And C# and is and. Yeah, that's C#. So that's logical and operator. This is a bitwise operator. So this is operating on bits instead of just like true false values. And how's it going, Mr. Julius? I hope you're doing well too. Wouldn't anding cube face with be something like, yeah. Yeah, that's what I was just thinking. So what I'm gonna have to do more likely is shift this left 7. 1, 2, 3, 4, 5, 6, 7. Yeah. And then I think it should be good. Yeah, I think that's basically what I want to do. Because then if we shift it left 7, it should, I think that's what I want to do. Let me see. Because shift operator is operating on bytes and stuff too. Yeah. I'll have to think about this just a little bit more to make sure that this is going to work right. But hopefully when we test it, we'll be able to find it. And wouldn't you want to shift it by 7 times 4 equals 28? Does the bit shift operator, okay, it's a bit shift operator, so I assume it's operating on bits, but I just want to make sure. Because I think you're right. So if we shift left 1, okay, so he says A equals that, B equals that. A shift left 1 is 10, which is, okay, yeah, so you're right. So we need to, okay, that makes sense. So instead of going by 7 times 4 is 28, we do that, and then we're actually going to go one more because it's the last 3 bits. Yeah, okay, thank you, Hilbert curve, because that is true. We didn't need that. Okay, so then here we can go texture ID, shifted left, and then this is going to be, we have 4, 8, 12, 16. So we'll shift left 16 and then we'll AND it with that and we should be good there. And this one, it's going to be shifted left 4, 8, 12. I'm just referencing my drawing too to figure this stuff out. And then this one should be shifted left 4. And this one should be fine as is. And then we'll have to do the reverse here. So we'll have to AND it by 0xFF, but then we'll have to say shift right 0, since that's fine. This one is going to have to be shifted left right 4, and this one is shifted left 12, right? Because 4 for each byte, which is 12. Yep. Okay, so that should be good. Then for the texture ID, we can do data and this, and I don't need a semicolon there. And I actually don't need brackets here either. We're just returning a number. So data and that shifted right, which is 1, 2, 3, 4 times 4 is 16. And then for extract face, we basically do this except backwards. So we'll say return. And then actually, I guess this should be a cube face. And we'll say change this to a cube face. And this is going to be data shifted right 29. ANDed, oh, and we're also, okay, yeah. So ANDed with this, then shifted right 29. So that way. Okay, cool. So, and then I'm gonna have to wrap this in parentheses so we cast the appropriate thing. Okay, so that should give us the same stuff. Hopefully we should get the reverse done and it should go forwards and backwards and we should be good. Now, let's just go ahead and try and do it. So I'll go ahead and say data equals, and then we'll say compress, and we'll give it the vertex, which is vert1 texture, and cube face, which is face. And we can do the same thing here. Data, compress, vert2, texture, and face. And same thing here. Except with vert3. And I was just thinking of something else too. So I originally said that we could upload the chunk position as a uniform, but I don't really think that's going to work right. Because if we upload that as a uniform, that means we would have to render each chunk. Oh yeah, we're already doing that anyways. Yeah, never mind, that's fine. I was going to say, then we'd have to make more draw calls, but that's fine since we're making one draw call per chunk anyways. So, yeah. We can ignore what I was just saying there then. Okay, and then we don't have to do this. So, this is what we do. Let's do a little bit of an assertion check. We'll say logger assert And we're basically going to check if we say extract face, or I guess position first, vertex cursor, yeah, vertex data, vertex cursor plus 0.data equals vert1 failed. Okay, so this is what we're going to do to sort of test this. We'll just go backwards, and if it doesn't work, then we should get an assertion failure. So we'll do 1, 2, 3. This should be 2, 3, 4. And then we can go ahead and do the same thing for our face. So this will be 0, and this should equal face. We should get the same thing for all of these. 1, 2, 3. Oh, and this should be data. So change that back. Okay, cool. So that should equal the face. It still doesn't like it. What's wrong with this? Oh, this should be extract face. There we go. So all that should work. And then eventually, once we get texture IDs, should be the same thing here. Extract text ID. And we should be able to do the same thing here. And this should equal to texture.id. So we'll do that. Failed texture ID. This is going to be failed face. And this is going to be failed position. Okay, cool. So hopefully that'll work. And put music in the background. Yeah, so I started experimenting with Twitch soundtrack, which is like a music thing, but apparently Twitch soundtrack, you can't upload those songs to YouTube, otherwise they'll be copyright striked. And I imagine YouTube audio library, if you use those songs and then put it on Twitch, it'll be copyright striked. So since they're kind of rivals, they don't like sharing stuff. So I still have to figure out something with how I'm actually going to do the sound and everything. Yeah. So I know other people have done it. I've just got to figure something out. I'll probably just end up getting like a bunch of classical music or something and playing that in the background, because that should be copyright free, right? Hopefully. Okay. Should we put the text ID assert after the UV assignments? Well, no, because this isn't doing anything right now. Since I don't know how I'm really going to do the texture ID, I'm just sort of, I'm stuffing it in here, but I'm just storing this normally for now. Yeah. Because I'm going to have to figure out how to like upload a texture map to the shader too, which I think I'm going to have to do through like texture, but we're going to be storing UV information, not actual texture, which is always weird and fun to deal with. So for now, it's just going to stay uploaded as extra data, but we're going to check and make sure that it's working properly. Yeah. Okay, so I guess let's just run this and see if we get any assertion failures. It's not going to work on the shader side for sure, but yeah, we're going to have to compile too. Oh, this must return a value. Return data. And what is this saying? This says using uninitialized memory data. That's fine. I guess we could initialize this to 0. That's probably a good idea, yeah. Okay, so it's not uninitialized anymore. So we should be fine. And how's it going, SE Woods? I hope you're doing all right. We're just figuring out how to compress data, which is very fun Bitwise stuff. Okay, so it looks like we got assertion failure. Which one was it? Failed on position. Cool. So we failed on the first one. What did it give us? So this gave us, who knows? Vert1 should be 0, 0, 0 though. Let's go ahead and we'll just stick a breakpoint. Right. Actually, I guess we'll stick a breakpoint right here and just make sure that it looks like it's setting everything properly. And we'll go from there. So, okay, so we go into here. If I jump into this function, we can see data right here. And you can see that data's value is garbage right now. So let's switch this to hex viewer because it'll be easier to sort of see if we're setting the appropriate bits. Where is this? I know you can view as hex somehow. Or at least you used to be able to. And you can't remember did much bit programming in Jade Engine. Yeah, I don't think we did do much bit programming in the Jade Engine just because Java doesn't make it very fun to work on a bitwise level. I mean, you can still do it, but it's not as opaque as C++ is, so it's a lot easier to do things like this. Oh, here we go, hexadecimal display. Okay, that makes sense. So if we do F10, this is all zeros now. That's good. But yeah. And is Albert Einstein? No, I'm definitely not Albert Einstein in programming skills. They're much more talented programmers than me. So, like, if you want to see a really good programmer, read about John Carmack. That guy is insane. Okay, so vertex X is just 0, so it's not going to do much, but it should only modify the first byte here, which I'm going to imagine it did. So it stayed 0. Then this should modify the next 2 bytes. Which, okay. So it definitely did something. What is Y here? Y is FFF. Okay, which is just, that's kind of weird. Because that looks like integer overflow. Oh, I bet you Y is -1, which that doesn't make sense though. It shouldn't be. Let's see. What is Y? If we go back up here, yeah, Y should just be going from 0 to chunk height. So we should be inside of here, which means if we look at Y, yeah, it should be just 0. What's vert 7Y? Let's see. Oh, you know what it is? I think we are getting overflow. Because if we take a look, wait, let's see, up here. No, right here. Okay, yeah, I think we're getting overflow. Yep, it's because of this. So Y is 0 right now. And if we think about this, if Y is 0 and then we do subtract vertices 0, which is 0, minus 1, what does that give us? That gives us -1, right? Well, what is -1 in signed bit integers? That's going to be 0xFFFFFF. So we can't have any negative numbers. So we need to modify this a bit so that we never get a negative here. Okay. Because if we do that, then we can't just have, we have to make sure that we're constrained to the range 0 to 255 so that we don't end up with weird cases like this. Otherwise, it's just going to be bad. So, yeah. So instead of doing this, which is where we basically say, we're going to +1 and then we subtract everything else, which is not good. Let's go back to my drawing of a cube and see if we can figure this out real quickly. So, right here. Okay. So right now, what I'm doing is having vertex 0 here. I'm probably going to just swap them all so that we don't have this problem. So basically, we're going to have vertex 0 here instead of 4. And then this is going to be 1 instead of 5. This is going to be 2 instead of 6. 3 instead of 7. And then this is going to be 4. This is going to be 5. 6. 7. That way we should get zeros all down here. And we might actually have to swap this too. So it should be 0, 1, 2, 3. Or I guess 0, 1, 2, 3. That way we're going positive directions every time. So yeah, so let's do that too. So instead of all of this, we are going to change this to, and this is going to mess with the way we're generating stuff too. So we're going to have to do a lot of rework, but that's fine. So this is going to be 0. This is going to be 1 because we need to go in a clockwise direction, I believe. This is going to be 2. This is going to be 3. So we're going to have to do 0, 1, 2, 0, 2, 3. And then we're going to have 4, 5, 6, 7. So we're going to have 0, 1, 2, then 0, 2, 3. So 0, 1, 2, 0, 2, 3 for the bottom face. This is going to be helpful, I promise. And then let's see. For the right face, or I guess we should do top face, which is 4, 5, 6, 4, 6, 7. So 4, 5, 6, 4, 6, 7. That is a horrible 7, which is going to be the top face. For the right face, we're going to be doing, we'll do 4, 5, 1, 4, 1, 2. 4, 5, 1, 4, 1, 2 for right. For the left face, we'll do 7, 4, 0, 7, 0, 3. For the front, we'll do 7, 6, 2, 7, 2, 3. So this is going to be front. See, when I do an actual series on this too, we won't have to redo this a million times because I'll just have the right one at the beginning. But I guess it's helpful to see how this works too. Okay, for the back, we'll do 4, 5, 1, 4, 1, 0. So 4, 5, 1, 4, 1, 0 is going to be back. Okay, cool. So I can reference that now as we're modifying things. So let's go back to this. And okay, what about the mobs AI? Will it be hard to implement? No, well, yes, but no, but I don't know really. So we'll have to see how we go with that. I think it's probably gonna be just a bunch of random, like, oh, should I move or should I turn my head? So it shouldn't be too bad. We'll get to that when we get to that. For now though, let's see. So verts 0 is gonna be XYZ, so that's fine. And then verts 1 is gonna be plus 1Z. So this is going to be 0. So plus 1Z. 2 is going to be 1 plus 1 in the x direction. So this could be plus now. 3 is going to be 0 plus 1 in the x direction. So that's also good. 4 is going to be 0 plus 1 in the z direction. Or I guess y direction. 5 is going to be 1 plus 4. Yep. So 5 is 1 plus 1 in the y direction. 6 is going to be 2. Yep. 6 is going to be 2 plus 1. And then 7 is 3 plus 1. Cool. So now we have gotten rid of all of our minuses. We shouldn't have any sort of integer wrapping. So we shouldn't have to worry about that 0xFFF thing happening. They should all be 0 to 255. Hopefully. If this all works right. I think we should be good. But you never know. Okay, anyways, so yeah, that's good. And we can go ahead and we're gonna have to modify the way we do this now too. Yeah, so top block ID is gonna be still the same, just X. Okay, yeah, but we're gonna have to, nope, that should be fine. Okay, so if not top block ID or top block is transparent, load block. Okay, and then we have to pass in the appropriate vertices. So for the top block, it's gonna be 4, 5, 6, and 7. So 4, 5, 6, and 7. So that should be fine. For the bottom face, it's now going to be 0, 1, 2, 3. So 0, 1, 2, 3. Hopefully this isn't going to mess with things too, because I have a feeling we're going to have to reorder these in certain ways. So I'm probably going to leave this 3, 2, 1, 0 because that's how it was before. So we'll change that to 3, 2, 1, and 0. And I think I'm gonna learn something with the series. Oh yeah. Okay, sorry, you misspelled learn, and I was like, wait, what? But yeah, I think that I'll probably learn a lot of things throughout this too. So every programming project, you get a little bit more knowledge about things, which is good. Okay, for the right face, we're gonna do 4, 5, or I guess 5, 6, 2, 1 or 5, 1, 2, 6. I'll do 5, 1, 2, 6, and hopefully that'll be good. Okay, and then for the left face, I will do 4, 0, 3, 7. 3 and 7. And for the forward face, we will do 7, 4, 2, 3. So 7, 4, 2, 3. And then finally for the back face, we'll do 4, 5, 1, 0. I have a feeling a lot of these are going to have to be changed, but for now, it's good enough. Okay, cool. So that should be fine now. We shouldn't have any integer overflow. So when we run this, we shouldn't have any problems. So if we go back into here and we run this, we're going to get to here. And then if we jump in, we can see that data is all zeros. So now if we look at X, zeros. Okay, so it's 1, which hopefully that makes sense. Y is 0, Z is 0. Okay, so if we do this, we should see the first bit switch to a 1. That's good. The next 2 bits should stay 0. That's good. The last 1 bit, or I guess the 4th bit should stay 0. Also good. This is 0 as well, so we're not going to have anything. The face is 2. So we should see this bit change to 2 shifted left 1, which is, what is that? So 4. It should be 4. Okay, cool. And we get 4 in the last bit. Okay, so that's a good sign. I guess we should just run this then and see what happens. No, we got an exception. Okay, what's happening? We failed on position. Which position? Okay, so it looks like we got past the first one. That's good. We just failed on the second one, which is, what is vertice 2? Let's see. So vert 2, it looks like it's just 1, 1, 1. Okay, let's see what's going on there. So if we go ahead and just put a breakpoint here again and get rid of that. Cool. So if we jump in, so vertex 1 looks fine if we jump in here. So X is 1, Y is 0, Z is 1. Okay, I think this went fine then. So let's see. If we jump out of that, yeah, okay, that was fine. We didn't have any problems there. Fine. So it looks like we're going fine for all of these. Yep, so it's going to fail somewhere else. I should probably figure out where it fails. Okay, so let me just remove this breakpoint real quickly. We'll continue. And we fail at, this is bottom block ID. Okay, so this is the bottom block for which X, Y, Z. So this is F, 0, 0. Okay, so this is 0, 0, 15. So we're on the last Z. So I have a feeling we're probably wrapping. Let's just put a breakpoint. We'll say if X equals 0 and Y equals 0 and Z equals 15, printf. This is just that we can add a breakpoint. So I'll put a breakpoint in here, and then we can jump into there and see what's failing. Okay, so let's jump into here, and then in load block, we go down here. So we've got 1, 1, 1, and I believe it's failing on the first one. So if we do that, that's fine. Okay, it's the second one that's failing. So let's look at the second one. Go back into here. Okay, load block. Let's go into here. Cool. So we get data. Data is 0. Vertex is 1, 1, 1. So when we do this, we should see 1 pop up in the first bit. That's good. When we do this, Y is 0. Okay, so we should see zeros for the next 2 bits. That's good. Z is 1, 0. Which means what? Z is 4, right? Yeah, no, because this is hex. So this means Z is 16. Okay, yeah, so we're getting some overflow. So what's going to happen is we're going to lose that bit, and it's just going to stay 0. Even though this shouldn't be 0. Okay, so got to rethink some things again, I think. Would I mind repeating what I said about bit programming in C++ versus Java and what is common? Your brother came in the door, just explained it last time. Yeah, so basically bitwise operations and stuff in Java is a little bit harder because Java doesn't like to let you know exactly what size your data is and everything. So like right here, I know I have an unsigned integer that's 32 bits big. So it's really easy to reason about this data. I know I'm going to have 8 bytes, which you can see here. I guess, yeah, no, 4 bytes, but 8 hex digits So I know exactly what to look for here. And I know that this is going to be interpreted as an unsigned integer. Whereas Java, all you have is int. And I think you can do lower level stuff and everything, but it's just sort of a pain to figure all that out. And Java doesn't give you a way to really figure that stuff out easily. So I prefer, if you're going to do bitwise operations, just do it in C++, because even though they both support it, it's much more intuitive with C++ than it is with Java to try and figure out what's actually going on under the hood. But yeah, for some reason we're getting a 16 value for Z though, and that is because if we look here again, so yeah, so as we get to Z is 15, let's see what's happening here. So Z is going from 0 to chunk width, which is 16. So we should stop at 15. But what happens is we actually get to 16 because we kind of need that last bit. Do we though? Yeah. So I think what's happening is as we get to Z is 15, what happens is we need the Z one more over for the right vertex, which is 16. Which means we kind of need like plus one more, which is annoying. So, and yeah, it's not 100% necessary when you deal with Java. Yeah, so you still can do it in Java and everything, but you know, it's just up to preference. So if you're fine with doing it in Java and stuff too, then you should probably do it. Like I imagine Minecraft probably has to do some bitwise manipulation to get something similar to this going on, because I have no idea what they do in their algorithm to compress the data and everything. But yeah, this is bothering me a little bit because we're gonna get wraparound. I'm trying to think of what I could do to mitigate this, but there's nothing really good. Let's go to the drawing screen and kind of figure this out. If adding 1 gives us overflow for the Z value, why don't we get overflow for the X value? We will. We just haven't hit that yet. So we should get overflow for X and Y. But since Z is the innermost loop, we're just hitting this one first. I'm going to go back to the drawing screen real quickly. Yeah. So what's happening is like, I'm just going to remove all of this because it doesn't really matter anymore. Okay. So basically, we have the blocks, right? So if, say, this is a chunk and a chunk looks really weird. If I can draw this right, let's get a box because that's going to turn out better than my boxes. Okay. So say this is a chunk, right? This is 0, 1, 2, 3, 4, 5, 6. And let's pretend this is the Z. Okay. Let's actually start this from 10 or 9. So this is 9, 8, 7, 6, 5. No, what am I doing? This should be 9, 10, 11, 12. Okay, so 10, 11, 12, 13, 14, 15. Okay, so basically what's happening is this is the Z. So we're looking at like the one face of a chunk. And for here, we get, oh, this left vertice is 9. The right vertice is 10. Then for him, he says, oh, mine is 10 and 11. So on and so forth. But then when we get to 15, he's saying, oh, my left one is 15. My right one is 16. And so we're getting overflow because even though we only have 15 blocks, or like we go up to 15, we need that one extra space for 16, and I can't tell if we actually do need that or not. Let's minimize this to 4 and see if we can replicate this a little bit easier. So if we have let's see, if we have 1, 2, 3, 4, and we pretend we only have 2 bits, can we encode all this information in here? So this is 0, 1, 2, 3, 1, 2, 3, 4. Okay, yeah, so we should, well, okay, yeah, so this is the problem. We have 1, 2, 3, 4 blocks here, but we have 0, 1, 2, 3, 4. So if we want to encode all of these positions into 2 bits, which is technically all we need, right? Because 2 bits equals 0 through 3. We're kind of missing out though, because we have this hanging edge for the very last block over here. So I'm trying to figure out, Hobson said that he managed to do this though. So, and SE Wood says you see that a lot of the variables using 0x in front of the values in JBox. Okay, yeah. So like I said, I imagine that Minecraft and other Java implementations and stuff use hexadecimal and like bitwise manipulations. It's just a little bit less opaque, so I don't like doing it in Java as much. But yeah, okay, so we basically have 0, 1, 2, 3, and then we have this hanging bit. So we actually have like 5 values, even though we only have 4 blocks, which is annoying because you would think there's a way to encode all of this into just 3 bits. I know we could do this a lot easier if we just used like a geometry shader and expanded this, except I've never used geometry shaders and I don't know how wide the support is, so I don't want to go down that route. Well, I think I'm gonna have to think about this one for a little bit, guys. So this stream was basically just sort of a random stream. I didn't plan on doing it. Just wanted to do it so that we can start working towards Twitch affiliate and stuff. But I think this has given me a good start for just sort of thinking out how I'm gonna approach this solution. And I'm going to think about this a little bit more and then come back to it later. Yeah. But thank you all for coming. I know we didn't make any progress this time, but we did because I have a little bit more of an idea of how I'm going to approach this. So it's still good. Hopefully in the next stream, we'll actually get the serialization done and we can actually generate large areas of chunks without using up 30 gigabytes of RAM. So hopefully that's what we'll get to in the next stream. Anyways, though, I'll see you guys next time. And thanks again for coming. Hopefully next stream will be a little bit more productive. Yep. All right. See you guys.